Okay, so before the commercials, I said that I gave a definition of what the weak derivative is, and I gave some motivation about it. But what we're going to do now is actually work out what the weak derivative is of some function, so we can actually get an intuitive understanding of how this thing works. And the reason I didn't rub this off the board is just by inspection on the board, we can get one of the really important cases out of the way first, which is if f is in L1 log and f actually has size of alpha derivatives, then we can just write right, remember this means the alpha-th derivative. So if that actually exists in the normal pointwise sense that we understand derivatives, then this must be true because this is just the integration by parts formula. Right? So all that can possibly go wrong in that case is each time I integrate by parts, I get a boundary term. And as someone pointed out in the break, these things are guaranteed to go away on the boundary. So that means that they disappear. So this expression has to be true. So big sigh of relief. If the function is differentiable and it's in L1 log, then its weak derivative is exactly the same as the strong derivative. So that was the easy case. It's also the case we don't really care about in finite element, right? Because what we wanted to know was how could we take some derivatives of functions that weren't normally differentiable. But it does mean that we understand that this is a strict extension of differentiability, right? It means that in all the cases where we knew what the answer was, the answer is what we think it is. And now we're going to make some derivatives make sense in some other spaces. So the next one to do is to say, okay, let's not be differentiable somewhere. And the simplest non-differentiable function, basically, is just one where we chuck an absolute value of x in one dimension. So let's try omega is going to be equal to -1, 1. So the length 2 interval containing 0. And f of x is going to be 1 minus the absolute value of x. So the reason we chose that one is because it is in fact the P1 basis function. Right? If I take the interval from -1 to 1, then this thing is 1 in the middle and it's 0 at the end. So we'd be really happy if we knew that that thing had a derivative and we knew about it. So the claim is that that derivative is what you think it ought to be. So what you think that derivative ought to be is that it's +1 here and it's -1 here. So the claim is that g of x is, which is equal to 1 for x less than 0 and -1 for x greater than 0, that is D1 weak of f. Claim. So, what do we have to show in order for that claim to be true? We have to show that the integral from, well, strictly minus, but they're going to put that in minus later, from -1 to 1, so the integral over the domain of f of x phi prime. So we want to show that that's going to be equal to the integral of g of x times phi of x with a minus sign out the front. So the trick here is this is an integral. We can do it everywhere ignoring points at which it's inconvenient. And the point at which this is going to be ever so slightly inconvenient is when we ask ourselves what happens in the middle there. And so all we need to do is cut the integral into 2 bits and add them back up again and do the 2 halves. So we do the integral from 0 to 1 of f of x phi prime of x plus the integral from -1 to 0 of f of x phi prime of x. So what are these equal to? So these ones, so f of x in each of these domains is completely differentiable, right? Because I've cut this to these two domains, and on the interior of those two domains, there's no problem with the differentiability of f. So now we use the trick that this was based on. We integrate by parts. So we can move this derivative onto f because that's a well-defined thing to do inside each of these domains. So that means that this is equal to, am I going to run off the recording here, or is that okay?
You're fine.
Okay. So that means that this is equal to minus the integral from -1 to 0 of the derivative of f of x. So the derivative of f of x on -1 to 0 on the left-hand interval is 1. Times phi of x. X. Plus, now I need the boundary terms, so that is f times phi integrated at evaluated at -1 and 0, and I'll put 0 minus here, right? Because you have to remember when you're doing these, this is now a boundary term, so it's actually the evaluation of f approaching from one side. Although it doesn't matter in this case, it will matter in the next example. And similarly, 0 to 1 of -1 times phi of x dx plus f of phi from 0 to 1. So, what can we say about these values? And this is the value coming from plus side. So when we evaluate f times phi at -1, that's on the boundary of the whole domain. So we've already assumed that phi is 0 there, so that term's 0. Similarly, when we evaluate f times phi at 1, that's at the other end of the whole domain, so that one's got to be 0. And what happens to these two now is, well, f's continuous. So f at 0 from plus side is the same as f at 0 from the minus side. And it's actually equal to 1 in both cases. And I get a +1 because this is the right hand of an interval, and a -1 because that's the left hand interval. So that means that these terms are actually cancelled. So what have I got in here? I've got a function which is 1 on the range -1 to 0, and -1 on the range from 0 to 1. And we already gave that function a name, we called it g. So this is equal to minus the integral from -1 to 1 of g times phi of x. Whoopsies, I've got an extra. dx. Solid proof. So, phew, really good news is we can have kinks in our functions, and we've got a concept of a derivative, which means that the derivative is what you hoped it was going to be. You just took the derivative inside the elements, inside the places where you needed it, and everything was great. So life's wonderful, and basically I just wasted an entire hour of your life explaining in a really long-winded way why it was you didn't even have to care about the derivatives. Well, if life were that easy, then Colin Cotter wouldn't have a job. Because it turns out to be the case that there are cases where this doesn't work. And so let's use an even simpler function. And in fact, it's the function that we would get if we decided to ask, what's the second weak derivative of f? So the second weak derivative of f needs to be the first weak derivative of g. So let's try and take the weak derivative of g of x. So, anyone here got an engineering degree?
So I wrote this one derivative in delta x.
So, what's this function called? Which is not quite. If I moved that to 0, what would this function be called?
Step function.
It's the Heaviside function, right? So this is the this is a very well-known function. And so let's do the same thing again, right? So let's step through the same steps and say g of x is equal to the function which is 1, or let's make our life really easy. Let's make it 0, because then we'll get the answer that the person in the corner is looking for. If I make that, so it's 0 for x less than 0, and 1 for x greater than or equal to 0, and we will make our domain omega is equal to -1, 1 again. So we're going to do exactly the same trick. We're going to say the integral from -1 to 1 of g of x times the derivative of our test function, which we're allowed to do because our test function is infinitely well behaved, dx, that's just equal to the integral from 0 to 1 of dx phi prime x dx plus the integral from -1 to 0 of dx phi prime of x dx. Wasn't that easy? And now I'm going to integrate. So once again, now that we've split that up, this is an incredibly well-behaved function inside each of those two. It's the simplest function you could possibly think of inside each of these. So I can definitely integrate it by parts. And so what I get is that that is equal to minus the integral from 0 to 1 of g prime of x, which is 0 times phi prime of x dx. Okay, so let's just get rid of that one because we already know that's 0. So it's just equal to the boundary terms, which are gx phi x from 0 to 1. And similarly, when I substitute in g prime x here, I'm going to get the derivative of this function. The derivative of 1 is also 0. So the body term vanishes, so I just get the boundary term. So I get g x phi x minus 1, 0. And now it really matters that I note that this is the right-hand limit and that is the left-hand limit, because they're now not the same thing. So now, as before, 1 and minus 1 are the boundaries of the domain, and on the boundaries of the domain we already know that phi of x vanishes. So that's great. But inside the domain, this is g of x, phi of x on the positive side, and g of x, phi of x on the positive side is 1. So that's phi evaluated at 0. and the other side, this is g of x, phi of x at 0 from the negative side, and 0 from the negative side is 0. Sorry, g from the negative side is 0. So plus 0. So the answer is phi evaluated at 0. It is at the bottom, that's right. And it needs to be as well because you need to have a minus sign out the front of your operator to get there. So, what this is saying is the weak derivative of g prime, of g, so we, I guess by logic, should call that h, but we're not going to call it h for reasons that someone's already let the cat out of the bag on, wants to be a function. And what I'm going to write down now is the conventional notation for what goes on now. However, to use the technical expression which the Stanford professor, who's done a wonderful series of online videos on this particular subject, does, is what I'm going to write now is bullshit. However, we'll write it down. The integral from -1 to 1 of h of x phi of x dx equals phi at 0 for all phi in the appropriate space, which in this case is d omega. This statement is complete bullshit. There is no function which satisfies this property. Right? And it's a really, really weird thing to have happen. Whatever I put in here, this function miraculously picks out its value at 0 when I integrate by it. This does not work. Those of you who have engineering degrees are sitting there going, of course it works. I know what this function is. They taught us about this function. Okay, so the alleged function, which this supposedly is something called the delta function. And it is said to be the case that the delta function has the mysterious property that if you integrate the delta function multiplied by any test function, then it produces the value of that function evaluated at 0. And people then say, okay, so how does this function look like? So it's a natural consequence of what and so it's a natural consequence of what you just wrote, that the function has to be 0 everywhere that isn't 0, because it doesn't pick up any values of 0 there. And it somehow has to integrate to 1 times the value at this point here. So its integral miraculously is 1, even though it's 0 almost everywhere. And so your bullshit meter should really be going off now, because we know that when we integrate, we're allowed to ignore values at individual points. But now we're being told that there's a particular value at this point. And so then the way that the bullshit merchants in engineering account for this is they say, oh, that's okay, because the function's infinite at that one point. So you say the delta function is this function which goes along and you go, that's the delta function. Okay, bullshit, 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 right? So all your reasonable definitions of functions say they don't actually attain the value of infinity at any particular point. If they do attain the value of infinity at some point by some definition, when you take the integral, you're entitled to ignore that anyway because you're allowed to go around, right? So this clearly is just not true. What is true is there is something usefully called delta, and it really does do that. And so if you look at a class of generalized functions called distributions, which are things that sort of look like functions, but you can't write them down by themselves. You can only describe what they do to other functions. In that space, delta makes perfect sense. Delta is the distribution which takes any suitable function and evaluates it at 0. That makes absolutely perfect sense, and that's really useful. And actually, Brad Osgood's lectures on the subject are brilliant, and I'll put a link in there, and anyone's got some spare time over Christmas, I really recommend looking at them. But it doesn't help us. It doesn't help us because that thing definitely is not a function. And it's really definitely not in any function space that we care about, right? Doesn't behave like any of the functions we want. So for the purposes of doing a finite element method, there isn't a useful weak derivative of anything that's got a discontinuity in it.
I can even take a derivative on.
That's right. That just told us something really important. That told us that this lecture was not a complete waste of time after all. It tells us that in the one-dimensional case, and what I might do is I might spend the last few minutes in a minute doing a brief excursion into our future in multi-dimensions to explain what might happen in more dimensions. But let's just think about the one-dimensional case for the moment. In the one-dimensional case, what we need in order to be allowed to take derivatives in our finite element spaces and integrate them and expect to get something sensible come out is we need continuity. Right? We're allowed to have only C0. We're allowed to have the finite element spaces we expect. So we can have finite element spaces that look like this. And actually, even when we go to higher order finite element spaces, they're still only C0 spaces, right? So the normal P2 space we use, the basis functions look like, there's one that looks like that, right? So that's really definitely not differentiable at quite a lot of points. And there are other basis functions in that space that look like this. And similarly, they're not differentiable at the endpoints. So even when we have functions which are higher order inside the elements, we typically have them be C0 at the endpoints. But that's all okay. We can take a first derivative in that case. You can't take a second derivative. So way back at the beginning, when we took our Laplace equation, and the first thing we did when we multiplied by a test function is we integrated by parts. So one of the reasons we were doing that was because if we want to work in the function spaces we're interested in, that second derivative doesn't make sense. The first derivative is discontinuous, the second derivative has got these guys in it. It's completely inadmissible. It doesn't work in any of the theory we've been doing. And so the reason why we integrated by parts was that then we had two functions which were being hit by first derivatives, and it was sufficient then for those functions to be in a nice continuous space, even if they didn't have continuous derivatives. And then we can make everything work out. In solids, when people are doing finite element methods for bending bars, and especially when they're doing finite element methods for making thin shells stand up, so if you want to work out the stresses in the Millennium Dome or something like that, then sometimes people will choose to use function spaces that are P1, so they are smooth at these points, which you can do if you jump through enough hoops. It makes the implementation hard, but you can do that. And that then means that you're allowed a second derivative in your operators, because the first derivative is C0, the second derivative is discontinuous, that's fine. So that is a permitted activity. Actually, I think I just lied. I think what we need to do is we need to use the last 10 minutes to talk about the Sobolev spaces that we're going to be in. And we will come back to what sorts of continuity you need in more dimensions when we do more dimensions, which will be after the break, after the Christmas break. So, what we can now do is we can go back to asking ourselves questions about which function spaces we wanted to solve our problems in. And so there's one general purpose function space that we've seen a lot, and that's L2 omega. And L2 omega is the space of square integrable functions, so it's the space of functions f such that the integral of f squared dx over our domain is less than infinity. So it has a finite value. You can do the integral doesn't come out to be infinite. And we've jumped through a bunch of hoops and shown that there are things we can do with that. Today, we've shown that being in L2 is not enough to be able to take derivatives. Right? The Heaviside function we drew on the board earlier, the function that's 0 up to 0 or 1 after 0, that's definitely an L2. Right? That's a really easy function to integrate, and integrating it square is also really, really easy. It's really clearly an L2. So L2 is clearly too big a space for us to do many of the things we want to be able to do. We need spaces which are smaller than that, which have some tighter properties that enable us to take the derivatives we want. Sometimes L2 is enough. So for people who know anything about discontinuous Galerkin methods, the discontinuous Galerkin basis functions are in L2 and they're not in any of the tighter basis functions, tighter function spaces we're about to talk about. And that has profound implications for the way the finite element, the discontinuous Galerkin method works. So now we've got our concept of a weak derivative, then what we're going to do is we're going to define a new norm. And this new norm is called the Sobolev norm. Sobolev is a 20th century mathematician, is really important in the theory of this whole area. And okay, you know you're in trouble when you start seeing subscripts and superscripts on the same objects at once. Just to raise the usual issue, this is the notation they're using in this book. I was checking another book about this lecture earlier, and they use the notation P, K up the top there. So when you start seeing these notation lying around in places, you do actually have to check how they're defining things, because mathematicians just can't agree. So this norm, with these two parameters K and P, is defined to be equal to the sum for the size of alpha, so this is going to be a multi-index, less than or equal to k. So this is where k comes in, right? So what does this mean? This means kth partial derivatives. So WKP means kth partial derivatives. Absolute value of weak derivative alpha of f So what happened in there? So for any given k, I take all the possible partial derivatives of order up to k, including the zeroth one, so we put in the integral, and I take, so that's what's in here, and I take the L-pth norm of it, and I sum them up to the power p and take 1 over p of them. It's like a p norm or p norms, which works out, they scale out. So, in particular, if I set k equals 0, then I get back the LP norm. Because if I set k equals 0, there's one thing in this sum. It's the 0th derivative of f. So I just get f in here. And I take the LP norm of f, and I raise it to the pth power, and then I raise it to the 1 over pth power, and I get back where I started from. So problem's over. So WP0 of omega equals LP of omega. Now you understand why mathematicians get into fights about notations, because someone's now going to say, oh, you're not being very consistent, because when you write W, you put P down the bottom, and when you write P, you put P up the top, and then someone says, okay, so you put the P down the bottom, and then you become inconsistent somewhere else. That's life. You just get to live with the confusion. So that's great. There's another case that we have seen as well, which is if we set k equal to 1, then we get back the Sobolev norm A, which we did in our original problem, right? So if you remember, we had A of u v was equal to the integral of phi of u prime v prime dx. That was in our original ordinary differential equation. So that is the inner product inducing the norm. So if I put just u in here, I get a norm now. And if I then take, so if I take the norm I already had, which is the L2 norm, so and I add this to A, so then over here I'll get u prime plus the integral of u squared dx over the integral. That is W2 1 of omega, right? So it's the L2 norm, the zeroth derivative norm, which would have a square root around it, but then I raise it to the second power, so the square root sign goes away. So it's that one, plus that one, which is the first derivative norm. And actually, to make this into W2, I actually need to put the square root over this, right? Because I'm going to get a 1 over p. And that's what makes the units come back out right, so that I get my norm behavior back. And so this now tells us what we were doing in the when we defined our space V earlier. So when we originally solved our previous elliptic equation, we wrote down, if I just jump forward to where it was, we wrote V is in a set such that A, V is less than infinity, and V had to be in L2 as well, and we also had to write that V0 equals 0. That was a boundary condition thing. So we'll come back to the boundary condition thing. If we basically add up those two statements, if we say that V is in L2, so V's L2 norm is finite, and its A norm is finite, that's exactly the same as saying its W21 norm is finite. You just added up two finite numbers. So what we really should have written was that V needed to be in W21 of omega, and also subject to the constraint V0 equals 0. So I'm not going to go into the fine detail of what happens on boundaries, but basically we've demonstrated that functions in this space have to be continuous, right? Because if they're not continuous, I can't take this first weak derivative. And so it's sufficient to just say what the boundary value is, because it will be continuous going down to the boundary, or equivalent to a function which is continuous going down to the boundary. So there's a technical argument as to why that's true, but it's basically a generalization of the argument we just saw about derivatives, so that works out. And just because we can't possibly have seen enough notation, there's a simplified notation. So it turns out to be the case, because in the finite element method we're using L2 norms all over the place, it turns out to be spectacularly important special case for the finite element method that this number here is equal to 2. So it's convenient to have a notation where that's not there. And the notation that's used, yeah, I know, I'm done, Andy.
Is that okay?
Yeah. The notation which is used is we use H. It's called H because it's a Hilbert space. We talked about them earlier. 1, because that power still matters. The H is sort of assumes the 2 of omega. Actually, the space of our continuous finite element spaces, which are, for example, sufficient to solve the elliptic problem that we've been doing in this course so far is called H1, and it just means W21, which means it's the space where we've got one weak derivative.
So presumably HK is W2K.
That's right. That's exactly right. So for the recording, someone's just said presumably HK is W2K, and that's exactly correct. Okay, we need to stop now because there's another meeting in here and we're out of time.